Hi again. I hope you enjoyed our previous lecture on the natural logarithmic function. Today we're going to look at some consequences of the integration formula that we developed last time. Because the derivative of log x is 1 over x, we now know that the antiderivative, or the integral of 1 over x, equals log x. We observed last time that the logarithm function, as defined by that integral, behaves much like pre-calculus logarithms. Today, again, we're going to use those formulas for developing some integration techniques. And the second part of the lecture, I'll begin my discussion of inverse functions. You might remember them, examples like x cubed and the cube root function are inverses of each other because one of them sort of undoes the other. And we'll come to those skills a little bit later in the lecture. So let's remind ourselves about our formulas here. We defined log of x to be the integral, the definite integral from 1 to x of 1 over t dt, and it was defined for x greater than 0. And from the second fundamental theorem of calculus, when we differentiate that integral, we get 1 over x as our answer. So the derivative of log x is 1 over x. And then we observe the following. Given the derivative formula, that gives rise to a corresponding integral formula. So the integral of 1 over x is log x. And we observed one more important point, that you're allowed to do this if x is negative, but you have to write your answer as log absolute value of x plus our arbitrary constant, of course. So please memorize the following formula. The integral of 1 over x dx equals the natural log of the absolute value of x plus c. Good. Let's do some examples. For instance, how about a very simple one, the antiderivative, or the integral of 2 over x? Well, of course, you would slide the 2 outside, and then you would have 2 times the logarithm of absolute value of x plus c. And oftentimes, you'll see this written a little bit differently in the back of the book, say. It might be written as log of x squared. What did they do? They moved the 2 in front up to the exponent, didn't they? And then you might have said, well, wait a minute, what happened to the absolute value sign? It disappeared. Well, x squared is already non-negative, isn't it? So we don't need the absolute value sign. You need that absolute value sign because you can never take the logarithm of a negative number, nor can you take the logarithm of 0, of course. So our final answer might be written as log x squared plus our constant of integration. How about the antiderivative of 1 over 4x plus 1? Well, I think you sort of know the tricks now. 4x plus 1 is going to be our u value when we do substitution, and its derivative is 4. And I'm missing a 4. So I put a 4 into the equation, into the integral, and I divide by 4 outside, so I don't change the problem. So I now have 1/4 times 1 over 4x plus 1, 4 dx. Now think in your head here. Let u be 4x plus 1. What's du? 4 dx, which is sitting right there. So the answer must be 1/4, that's sitting out in front, natural log of the absolute value of 4x plus 1, plus our constant. And of course, you can differentiate that, and you'll see that you got it right. How about the integral of secant squared divided by tangent? Looks pretty complicated, doesn't it? Looks kind of messy. Well, think of it this way. Let u be tangent. What's the derivative of tangent? Secant squared. So this can be written as 1 over u du, can it? I've got the derivative sitting in front of me. So the answer is log absolute value of tangent plus c. Isn't that neat? And again, you can check it by differentiating. Let's do an area problem. Remember, the area problem was one of our fundamental classic problems when we introduced the integral calculus. How about finding the area bounded by the curve y equals x over x squared plus 1, and the x-axis, say, up to x equals 3. Here's a picture of that region. There's the curve x over x squared plus 1, and it intersects the origin, and I'm going to find the area out to x equals 3. Good. So the area would be the definite integral from 0 to 3 of x divided by x squared plus 1. Kind of same kind of thing we just saw earlier. I'm going to let u be the denominator, x squared plus 1. Its derivative is, of course, 2x. I'm missing the 2. Put a 2 in there and divide by a half, or divide by 2 outside. And we have 1/2 integral from 0 to 3 of 2x over x squared plus 1. That's precisely in the form of 1 over u times du. And hence we have as a final answer of the anti-differentiation part, 1/2 log x squared plus 1. And we evaluate that between 0 and 3. So first we plug in the 3. And so we have 1/2 log of 3 squared plus 1 is 10. And we subtract when we plug in the 0, and that would be log of x squared, log of 0 squared, plus 1, which is the log of 1. What's the log of 1? 0. So our final answer is log 10 over 2, which turns out to be approximately 1.151. That's how much area there is under that curve. Good. I hope you sort of saw here that these integrations are pretty hard. It's often not clear how to proceed on an integral problem. We do have a lot of formulas, and we've memorized some formulas, and our workbook has a list of important formulas that you definitely should memorize. But a lot of integral problems require some cleverness. There are many, many methods of integration. I remember when I was a student, the professors would do integrals at the blackboard, and I was always amazed at how they could figure out how to do some of these problems. I always thought they were just geniuses because they had all these tricks in their back pocket. Now that I've taught calculus for a while, I realize a lot of that is, of course, memory and, of course, even more important, practice. The way to become good at integration is to practice, practice, practice. So I'm going to show now some problems that you might sort of say to yourself, wow, how did you do that? That was really amazing. You're really clever, Professor Edwards. Well, no, it's because I've practiced this skill a lot. And if you practice, you'll get very good at it too. So let's look at some problems that are not quite so obvious. Suppose you have a differential equation, dy dx, or in other words, y prime, equals 1 over x log x. What's the function y? Let's solve that differential equation. Well, of course, y is the antiderivative of 1 over x log x. So we have to anti-differentiate 1 over x log x. And I hope you tell yourself, you're sort of saying, it's not obvious to me what to do here. But let me show you a way to think about this. Write it as 1 over log x times 1 over x dx. And let u be log x. So u's in the denominator, log x. So I have 1 over u. What's du? What's the derivative of log x? Oh, that's 1 over x, which is sitting right there. I've got du right in front of my eyes. So this problem is 1 over u du. And what's the antiderivative of 1 over u du? It's the logarithm of u. So our answer is the logarithm of log x. And of course, I put absolute value signs around it, as we always do. So the final answer is log x plus c. Isn't that a curious quantity? Logarithm of the absolute value of the logarithm of x. Log. Strange. Let's verify it. Let's make sure we got it right. What do you do to verify an integral problem? You differentiate your answer. So what's the derivative of log of the absolute value of log x plus our arbitrary constant? Well, think of this as log of something. Log of something. So it's 1 over that thing, that's something, so it's 1 over log x, and then by the chain rule, it's the derivative of log x. And what's the derivative of log x? 1 over x. So I finally get 1 over log x times 1 over x, which is the original integrand. Isn't that amazing? Good. Now, we have the opportunity with this integral of 1 over x to find the antiderivatives, the integrals of the remaining 4 trigonometric functions. You remember we did sine and cosine earlier because we know their derivatives and those are very simple. But how would you find the antiderivative of tangent? What would you do? Well, write tangent as sine over cosine. Okay, so it's sine over cosine. And now I think you can see what's coming. I'm going to let u be cosine x, the denominator. The derivative is minus sine x, and that's sitting in the numerator except for that minus sign. So I take my original problem, which is sine x over cosine x, and I introduce a minus sign inside the integral sign and another minus sign outside so I don't change the problem. And now I have minus the integral of minus sine x over cosine x. U is cosine, du is sitting there, minus sine x dx. So the answer is minus log absolute value of cosine plus c. Isn't that neat? And by the way, you might see this written differently in some textbooks. That minus sign in front of the logarithm is really a minus 1, isn't it? It's minus 1 times logarithm. And that minus 1 can be an exponent. You can slide that up to be an exponent on the cosine. And what's cosine to the minus 1 power? That's 1 over cosine, also known as secant. So you'll see this sometimes written as the integral of tangent is the logarithm of the absolute value of the secant function plus our constant. Good. Another antiderivative that we need to know is the antiderivative of secant. And it has the strangest answer of all. The integral of secant is the natural log of the absolute value of secant plus tangent, plus our constant. Well, how do I know that's right? You can check it. Just differentiate that answer and you'll get secant. So it must be right. A better question is, how did they ever come up with this answer? It's easy to check it that it's right. How'd they ever come up with it? If you open a calculus book and look at the chapter on logarithms, you'll see a trick they use. What they do is they start with secant and they multiply numerator and denominator by secant plus tangent. Wow, so they fatten it up a little bit. They make it a harder problem, and then it turns out the answer just appears. So it's kind of an amazing little derivation. I don't think it's important to know, but I do suggest you memorize this formula because every so often it occurs in calculus problems. The other two remaining trigonometric functions, cotangent and cosecant, of course, they have antiderivatives as well. Those are not so important. You can look them up in any text, but I also think you know how to do them probably. At least cotangent's pretty easy. It's the same way you did tangent. Cosecant's a little more complicated. Let's do an average value problem. Here's an old skill. We talked about the average value. It was part of the mean value theorem for integrals. Let's find the average value of the tangent function on the interval 0 pi over 4. Now I know something ahead of time. Tangent of 0 is 0, and tangent of pi over 4 is 1. So I know my answer, the average height of the tangent function, must be between 0 and 1, because it's 0 here, and then it's 1 over here. It's somewhere in the middle. Here's how the formula goes, if you remember. It's 1 over the difference in the endpoints, so it's 1 over pi over 4 minus 0, and then you integrate tangent over the interval 0 to pi over 4. Well, the first thing I'm going to do is that 1 over pi over 4, I'm going to flip that fraction up to be 4 over pi. And the antiderivative of tangent, we just did that, is minus log absolute value of cosine. And then we plug in the endpoints 0 and pi over 4. So I'm going to move the minus sign outside to make things a little bit simpler. So I have minus 4 over pi, and now I have the logarithm, and I plug in pi over 4. Watch how I do this. What's the cosine of pi over 4? It's square root of 2 over 2. So I get logarithm square root of 2 over 2. Now I have to plug in 0. Well, what's cosine of 0? 1. So it's minus log of 1. Good. So I've plugged in the endpoints. And now my answer is, when I simplify, minus 4 over pi logarithm square root of 2 over 2, because the log 1, of course, is equal to 0. And then I punch this on my calculator, and I get an answer of about 0.441. Now, you might be looking at that and say, wait a minute, Professor, wait a minute. That expression, minus 4 over pi times the logarithm of square root of 2 over 2, that looks like it should be a negative number. It's got a minus sign in front of it, doesn't it? It looks like a negative number. What's happening here? Can you see why it's really a positive number? Well, here's the reason. Square root of 2 over 2 is less than 1. So the log of square root of 2 over 2 is less than 0. So that's also a negative number, and negative times negative makes positive. So I was fooled for a moment, but now I see why it really is a positive number. Okay, here's another example of a function or an antiderivative problem that makes professors look real smart. Let's try to find the antiderivative of x squared plus x plus 1, all divided by x squared plus 1. And my first reaction to this problem is, I don't have any idea how to start. What do I do with that globular mass of a polynomial divided by a polynomial? Ouch. What can I do? Well, one thing you can do is long division. I'll talk about long division in a moment. If you divide the denominator into the numerator, you obtain 1 plus the remainder x over x squared plus 1. You can see that another way in this problem. Look at the numerator. It's x squared plus 1 plus x. Take that x squared plus 1, match it with the denominator. That gives a 1, and then left over is x over x squared plus 1. However you do, now I have a new problem that I can do. The antiderivative of 1 plus x over x squared plus 1, well, the first piece is easy. That's the antiderivative of 1. That's going to be x. And the second one, we've seen problems like this before. The bottom is x squared plus 1. That's my u value. Its derivative is 2x, so I stick a 2 in there, divide by 2 outside, and I get x plus 1/2 log of the denominator, which is x squared plus 1 plus my constant. Uh-oh, I didn't put absolute value signs around that answer. Why not? Well, x squared plus 1 is always positive, isn't it? So I don't have to worry about the absolute value signs. And this problem, I mentioned long division. And I sort of have a question I always ask my students when I'm teaching calculus. Did you study long division in high school or in middle school? And I'm getting interesting answers. More and more I hear, No, professor. What is long division? I've never heard of it. Blah, blah, blah. It turns out in college, in calculus, you need long division sometimes to do some of these calculus problems. So I wish they would still teach it in the high school and middle school years. Good. I'd like to now sort of change gears a little bit and do a quick review of a pre-calculus topic, although I'll mix in some calculus. We're going to need this topic when we find what we call the inverse of the natural logarithmic function. And that function will be the exponential function. But to get there, I have to kind of review a little bit about inverse functions. You might remember, for example, that the trigonometric functions have inverse trigonometric functions. And those functions kind of undo each other. The sine of the inverse sine, things like that. We'll study inverse trig functions a little later. So what are inverse functions? Here's the formal definition. We say that a function g is the inverse function of the function f if the composition f of g of x equals x for all x in the domain of g, and g of f of x is also equal to x for all x in the domain of f. In other words, if you first do g and then do f, you come back to where you started from. The two functions kind of undo each other. Okay, I'll show you some examples in a moment. Now there's a notation for inverse functions, and it's f to the -1 power, and that's a lousy notation. It's sort of sad that all through math and science, every so often we have some bad notation. This notation's bad because you might confuse it with 1 over f. Remember, when something to a minus power, that means it's in the denominator? We don't mean that in this case. We don't mean 1 over f. When you write f to the -1, you mean the inverse of f. It's an unfortunate notation and can be confusing at times. So we have to keep aware of our situation. This happens a lot in mathematics. For instance, we use 3 different words in calculus to say the same thing. And it's very confusing for students. We say that 2 things are perpendicular, and we also use the word orthogonal and the word normal to each other. They're normal to each other. All 3 of those words basically mean the same thing. And yet we have these 3 different words. And it's kind of sad. I wish we had just picked one word and stayed with it. Let me give you an example of some inverse functions. X cubed and x to the 1/3 power, in other words, the cube root, are inverses of each other. For example, if I take 2 and cube it, I get 8. And if I take the cube root, I'm back to 2. Okay, you see how it works? You apply one function, it gives you a number, you apply the other function, and you come back to where you started from. Look at x squared. It's a function that it does not have an inverse. You might think it's the square root of x, but the trouble is x squared is not a 1-to-1 function. Remember, it's our parabola. And so it will be okay as the inverse of the square root function if you restrict x squared to x bigger than or equal to 0. But otherwise, it's not going to work. Okay, so there's an issue here about not all functions have inverses, and sometimes you have to restrict domains. Let's do another example. Let's look at the function 5x plus 1, f of x, and g of x is the quantity x minus 1 divided by 5. I claim those are inverses of each other. Now, how would you verify it? Well, you would do the definition. You would form their composition. So f of g of x would be, watch how you do this. It's f applied to the result of g, and g does what? G is x minus 1 over 5. So now I have to take f of the quantity x minus 1 over 5. Well, what does f do with something? It multiplies it by 5 and adds 1 to it. So I'll take that quantity x minus 1 over 5, multiply it by 5, and then add 1. And now look what happens. Miracles occur, the 5's cancel, and then the 1's cancel, and I'm left with x. So the composition yielded x. And you can do a similar argument the other way. G of f of x is also x. Let's look at the picture of those two functions. F is labeled as a straight line, 5x plus 1, and the other function is also a straight line. It's x minus 1 divided by 5. And look how those lines appear in the graph. Do you notice anything here? Well, they're symmetric across the line y equals x. There's some nice symmetry here. This always happens with inverse functions. There's a symmetry across the line y equals x. Here's another question we can ask about this. How are the slopes related between f and its inverse g? Well, look at this example, this very simple example. The slope of f is 5, and the slope of g is 1/5. Can you guess the theorem? The relationship between the slopes, they're reciprocals of each other, aren't they? If one of the slopes is 12, the other one is going to be 1/12. That'll come in handy a little bit later. Good. I mentioned this earlier, but given a function f, it will only have an inverse if the function is 1-to-1. Okay? Keep that in mind. You must be 1-to-1. You must pass the horizontal line test. Good. Let me show you an example of a function that's not 1-to-1, but we can do some surgery on this function and turn it into a 1-to-1 function. It's our old friend, the sine curve, f of x equals sine x. Here's a picture of sine x. It's that wavy curve. It's not 1-to-1. It does not pass the horizontal line test. So it's not going to be invertible. It does not have an inverse yet. So what do? Well, we can make it 1-to-1 if we restrict the domain. So in this picture, I've shaded in the part of the graph between minus pi over 2 and pi over 2. And on that piece of the graph, indeed, it's 1-to-1. Now it passes the horizontal line test. And that is sort of the technique for defining what we call the inverse sine function. And tune in to a later lecture when we'll spend a lot of time on the inverse trigonometric functions. Great. I'd like now to ask you to answer some questions. I like to pose these to my students when I'm teaching calculus. I'll walk up to a student and say, hey, what do you think about this? Put them on the spot. And here's my series of questions. I'm going to give you a function, and I'm going to ask you, what technique would you use to integrate, to find the antiderivative? And maybe we won't do the problem out completely, but we'll see what the algorithm is, what the technique is to find the antiderivative. For instance, if I gave you the cube root of x to the 1/3 power, how would you find its antiderivative? What would you do? X to the 1/3 power, but I've written it as the cube root of x. Well, I hope you would say to yourselves, oh, x to the 1/3, that's just a power rule. And it's no problem. It would be x to the 4/3 divided by 4/3 plus a constant. Good. How about this one? Suppose I gave you x squared divided by x cubed plus 4. Any ideas? Yeah, it's going to be a logarithmic function, isn't it? We're going to let u be the denominator, x cubed plus 4, and the derivative of that denominator is 3x squared, and I've got it in the numerator except for the 3, so I think you see the game here. Here's another one. How about cotangent? How could you integrate cotangent? You could have memorized the formula for it, but I have a terrible memory. So when I see a problem like cotangent, I go back to the skill of, well, how did we do tangent? Oh, we wrote it like cosine over sine. Well, cotangent is cosine over sine. And now it's going to be some logarithm, isn't it? I'll let u be the denominator, and the numerator is just sitting right there. So the antiderivative of cotangent will turn out to be a logarithm. Great. Good. I think we've covered a lot of material today, both on the use of the integral formula for 1 over x, giving rise to a lot of logarithms, and a brief look or a brief review of inverses of functions. Next time, what we're going to do is a very exciting lecture, I think. We're going to take these ideas and find the inverse of the natural logarithmic function. This function will be called e to the x, where e is that very famous number, approximately 2.718. And that will be the inverse of the natural logarithmic function. And we're going to play with this new function called e to the x, and we'll discover something quite amazing about its derivative. But you'll have to wait till next time. Thank you very much.